At first, let me explain an engineering problem that we have here. So we have a source, DC source, and we have a load. Load resistance is much greater than a source resistance, so actually current that flows in this circuit is designated by this load resistance. For some reasons we have now a short circuit here, and when we have a short circuit, obviously this current is designated only by this much smaller resistance. To prevent a rise of this current, at first a breaker is connected in series, and also you have to connect reactor inductance. Why? Because each breaker has some delay time. It breaks after 20 microseconds, and we don't want current to be greater at this 20 microseconds as 20 milliamp. Actually, we want this current to be exactly 20 milliamp, and our task is to size this coil, this reactor inductance. Okay, let me repeat. When connected in series with a load of variable resistance from 100k to 0, a coil tries to maintain a constant current flowing between its terminals, obviously for some time only. So this is the manual solution, calculations that are terminated with these values. So we have exponential curve, exponential rise. Obviously this current is not rising to 1 amp because we have a breaker, and at this level, after this time, the breaker opens a circuit, so this current then drops immediately to 0. A calculation by means of PSpice. This is PSpice non-schematic version. I'm going to skip. We have to use a performance analysis. Let me show how to do this using a schematics version. So we have to draw a circuit diagram. In case of our coil that we are sizing, value of this coil, then we have to set a value as L variable in brackets, and also, as we don't have any more a switch here, we have to set initial condition of 1 milliamp calculated before, around 1 milliamp. This is 100 volt divided by 100k connected here before then. Analysis setup, transient analysis, final time, as we are actually I will final time is enough to set this time greater than 20 microseconds, let's say 21 microseconds. Well, step ceiling not necessary, let's say 0.1 microsecond, and then parametric analysis, variable resistance, a global parameter, decay strip type, and it is a matter of experience. Let us assume that this value is between 50 milliamp sorry, and 500 milliamp. For the accuracy of calculations, let us assume 1000 points per decade. Then we have to save all this data and press start simulation. When simulation is completed, we have to accept all values of variable inductance. Then we have to perform this so-called performance analysis. We have to replace this time by inductance, and on the vertical axis we have to set a value of current that flows through a mesh current, doesn't matter this or this current, at the time of 20 microseconds, which is our task. So this curve is current at 20 microseconds, and then we are looking for the level of 20 milliamp to find the proper value of a reactor inductance by means of search forward level command 20 milliamp. We find that this value is 104, which is obviously the same as we have received before. Now, very briefly, live version. Circuit diagram stored in computer memory. Our inductance, its value L var, its initial condition calculated before, it's 1 milliamp. analysis setup, transient analysis, okay, and parametric analysis, LVAR, and these values. Okay, then after saving these data, we may start the simulation. And after a few seconds, it is quite a number of calculations, we are asked whether we want all values of inductance. Yes, okay. And we have a probe in window, blank probe window with time on horizontal axis. We want performance analysis. We want to change this time into inductance. So now we have inductance, and then we have to add trace, to obtain on a vertical axis a current Y, current at 20 microseconds. That way, this is plot of current, mesh current at 20 microseconds. We are looking for the level of 20 milliamp to find the proper value of inductance. We can do this by means of toggle cursor and search for that level. M is our level, and we have obtained this value for 20 milliamp. This value is 104, sorry, this is 20 milliamp, 104 millihenry. That way we have completed simulation.